Tonight we're going to look at FRC Vision Systems. We'll look at some of the ones that we've used in the past and how it's developed over the years to where we are now, so we have some idea of like why we use the things that we use now. And we'll look at some of the technologies that we're using now to be able to use vision and cameras to help our robots play the game. So let's start with some of our past systems. So we're going to go way back. So I believe it was the first vision system to be introduced into FRC. I could be wrong. There could have been something before this, but I don't think so. There was a CMU cam introduced in like 2005, 2008. So this was back when I was in high school. It was sort of able to see color. It really didn't work well. So down here in the bottom left, we have the 2005 vision targets. They were just like green panels painted on the game objects. And a couple were scored all season, if I remember correctly. It was not a very often that they were scored because they were like randomly placed on the field, and then your robot was supposed to track the green, pick it up, and then score it, which at the time was not something robots could do. In 2006, it got a little bit better. For 2006 and 7, they put like actual green lights on the field. That was definitely better than just the green object, because like different lighting and anything messed this up a lot. The lights on the field were definitely a little bit better. So there were some robots that did use it to aim into the goal for 2006, and that worked okay. And I think they used it in 07 as well. You had like this little like sheet metal bracket with servos that you were like mounting it on, and it would drive the servos to point at the object, and you could like tell from the servo position like where you were supposed to like turn. It was very weird, but it did work a little bit. But it was still pretty hard to do. Not a ton of teams were doing it well. A lot of times in games, it was easier just to like drive up and get centered and score in whatever the goal was. Moving forward a little bit into like 2009 and 10, this is when we got into the C-Rio control system. So this is the first time we had like a National Instruments controller, which is the same people who build the RoboRio. And so we had a little bit more ability to do things. It was a slightly faster processor and things. So in theory, you could do more. It still didn't work very well. In 2009, they got rid of the actual glowing lights, and they tried to go back to just like solid color targets and things, or shapes, and it still didn't really work. So there was a few teams who could color track the different patterns here of like the pink or green. So the blue one had the pink on the bottom and the red one had the pink on the top, and it kind of worked. The Axis camera itself was like a network camera. There were a couple different versions throughout the years. You could use it to like stream video back. In theory, you could do some amount of color tracking on it. There were some other devices at the time that weren't like in the kit of parts that could let you do some amount of color and shape tracking again, but nowhere close to what we're able to do now, and really not all that functional for most teams. There were a few teams who were doing some more advanced stuff back then and could kind of get things working. But most of the time, even as like once the pilots took over, the drivers took over, they were still kind of doing almost all of this by eye. They weren't really using it to automate the robot functions all that much back here. When things really started to change was when they introduced the retroreflective targets. And so this changed how the cameras could actually see the actual targets themselves, because you would have lights basically surrounding the target. So up in this like top right, you have these ring of LEDs. So we would have ring lights, and so they would put out a bunch of green light directly like around the actual camera lens, and the targets themselves on the field would be retroreflective. So any light that shined on it, just like the highway markers and things, shine directly back. And so this let them light up really brightly inside of the camera. The camera could see it super brightly compared to everything else around it that would be dimmer. It would also light up green, so you could like color, you could mask everything to only show you the green object. You could have like a green blob on your screen, and you could tell it to like center that green blob, and then you could use that to score. So this definitely got a little bit better. Um, it did mean that the robots all had these like super bright green lights on them. And so as we went forward from 2011, this was the standard. Like we even had retroreflective all the way back until 2023. Um, those green lights meant that it was like weird rules, and there was always a little bit of contention because if you had super bright lights and they were shining at the other teams like drivers, it would make it so where they couldn't see the field, which is not what you want. And so there was always a little bit of contention of like how bright are your lights allowed to be? How often are they allowed to be on? Can you run them the whole match? And like different robot inspectors or different referees or FTAs would all have like slightly different takes on how bright your lights could be and how often they could be there. And if some drivers complained that your lights were too bright, they could be annoying. And you'd have to figure it out through the event. So like from event to event, it could be different whether you could have bright lights or not. It was all very frustrating. And this was, over a decade we were basically dealing with this, trying to figure it out. For some games, it ended up being easier for a lot of teams. Instead of having like the actual cameras and lights doing any sort of auto aiming, they would literally just mount flashlights, or even in 2012, I don't know if teams did it after, they would use literal car headlights on their robot. And so they could tell where their robot was pointing just because it had a super bright light pointing at the object, and it would retroreflect enough so even from like the driver station, you could see where the robot was pointing. And so teams were doing this in basically every launching game, every shooting game from 2012 through 2022. There were some teams still just using the flashlight to be able to like aim their robot at the goal. Um, this normally wasn't as quick or precise as we can do it with automated aiming now. We can know exactly where the goal is, and aim at like different parts of it or swing around really fast until we get there. And we can do a lot more with the modern vision systems that we have now. But the flashlight was a super cheap, easy, and reliable way to aim robots for a long time. And there still may be a game where it is valuable to have a flashlight on the robot, and shine a bright light in a narrow beam. And there's some different like motorcycle headlights and some different cheap ones. We've had them on our robots at different points that let you kind of see a cone or a beam of light that's a pretty narrow, and kind of see where your robot's pointing. Um, I think we even used it in 2017. We had them kind of running along the ground, so you'd have like this like beam of light stretching on the ground. Because in 2017 there was like basically at some point your robot would go behind these giant airships that were in the middle of the field, and you wouldn't see your robot, so you wouldn't actually know which way it was pointing all the time. But if you had this beam of light coming out, you could kind of tell which way it was going to come as you drove behind the airship. So we had things like that running as well. So there's a lot of times where some flashlights end up helping, even though they're not actual cameras and vision systems. Just using the humans and the drivers and helping that way does help. Um, so as we got further along, you can kind of see what the vision systems actually see. So this was the 2016 game. The retroreflective target had this like U here, and you can see it does kind of light up green a little bit, and it's able to decide that, yeah, this is the target I want to be aiming at, and then kind of center that, and your robot can launch the ball into what was the goal here. It's a little hard to see in the shadows, but there was an opening here that you had to launch the boulders through. Um, And so this is kind of what they're seeing in that vision system. So it did work relatively well. Um, we were able to use webcams directly on the robot in 2015 when we got the RoboRio for the first time. So we got a new control system in 2015, and it made it a little bit better. But there still wasn't really enough processing power on it to do really complicated vision processing directly on the robot's processor. You could relatively reliably send a video stream back to the driver and like have it displayed on the driver station laptop, which was still a pretty good um, advancement. Like for relatively cheap, the Microsoft little webcams came in the kit of parts. You could pretty reliably plug that into your RoboRio and get a pretty small pixelated stream back to the driver station, and it worked okay. As other teams started to make more advanced features, one of the most notable ones, there were quite a few teams doing different things, but in 2016, the Cheesy Poofs actually mounted an Android phone on their robot, and had the vision processing and everything running on the phone using the Android cameras, and then sending that data back to the Rio over a USB connection. And so they had software running on the Robo Rio that could talk to the Android phone, get that aiming data back, um, and do it that way, because there just wasn't really a lot of small other computers that you could nicely mount to the robot and do vision on, back then. Like the Raspberry Pis were just kind of coming out, and so they didn't really exist to do nice vision yet, um, in this time frame. They sort of did, um, and so we moved a little further along. We got the Limelight actually came in to exist as a company in 2018. And so this was the first fully integrated package that had the super bright green LEDs built in. It had the camera. It was a network device. It was designed to be powered off the robot's battery, so it doesn't like restart in the middle of the match or anything when the battery voltage gets a little low. Um, it had the ability to stream an extra camera, so you could plug in a USB camera directly into this, and it would do the network streaming for you, so you weren't having to do that part on the RoboRio either. So you could have like a front and back camera, because you could still look at, what the Limelight was seeing, but you could also have like an intake camera or whatever else you needed. And so this was a really big deal. Just there was a technology jump a little bit here. It ended up being a little bit of a soft launch because there wasn't much the vision system needed to do in the 2018 game. 2018 was the game where you had the milk crates, power cube things, and we were putting them on those big, balance beam seesaw, objects. And so they didn't really have vision targets to help you aim very much on those. There were a couple vision targets on the switches, but they weren't all that helpful. Um, so they weren't too useful. We did buy one that year, and we had one on a robot, but it was mostly just for, the driver streaming, so we could like see it as an intake camera and everything, and use the video coming back for the drivers, not actually doing any of the complicated, um, aiming or anything yet, or any of the automation that we'll be able to do with cameras coming up in a few years. Um, and so there was a little bit more, um, just kind of how we progressed from there once the Limelight 1 existed. Um, 18 to 22, retroreflective tape became very standard in all the games, and we had a lot of bright lights. So now Limelight had released their version 1 in 2019, or 2020. They released a Limelight 2 that was a little bit smaller. I think the lights even got brighter on that one. Um, and so it was just a lot of that, and you started needing to be able to aim a lot more to keep up, as it was just the way the games were designed and what teams were able to do with that vision tracking. You were able to do a lot more of your scoring with the vision system. So in 2019 especially, we had those pretty good vision targets, and it was really useful to be able to have it track and just like drive your robot into the scoring location with each of those vision targets. And you could be a lot faster that way. And then 2020, even more so, when you had another shooting game, and we had all of this technology at that point. So we were aiming at the goal very reliably with the vision system at that point. Um, One of the other things that came out around that same time in 2019 was, WPI Lib made a Raspberry Pi image that allowed it to very easily do, um, some some of the things the Limelight did. So you could stream back the network cameras very easily that way, and you could run some amount of, tracking and vision, OpenCV, computer vision software on that Raspberry Pi, and getting some of the same abilities that the Limelight had. But it still wasn't really all that user friendly, um, but it did work a little bit. Into 2020 and 2021, during the missed year when we didn't have a full season in 2021, Photon Vision was fully released, and at that point you could fully have, software running on a Raspberry Pi that was very close to doing the things that the Limelight devices were doing, and largely for a lot less money. Um, so basically, every Limelight that has come out, besides for the one that was just released for FTC, has cost about $400, like $399 or whatever. And so they aren't cheap. Um, so it was kind of pricing some of the teams out who didn't want to invest that much just into that vision system. Um, you are paying for a good amount of like their software development, because it is all an all-in-one thing. You can basically, once you get it imaged, it's relatively easy to go into their software and like move the you're kind of just moving sliders and setting some configurations and things, and it's sending back like where the center of the target is and things, so you can just use that in your code to be aiming and things. So it's a very, very simple all-in-one solution, but it does have some amount of limited flexibility. You can't like change the software yourself or anything, and so as teams wanted to have a little bit more control or wanted to save some money, the open source solution Photon Vision allowed a lot of those teams to do that. So you could have different cameras. You could potentially have multiple cameras running off of a single computer that you had mounted in your robot. So there's a lot of different things you could do um, with Photon Vision. And now that we kind of had those two different systems in place, teams are starting to want to do more with Vision. So a couple things I didn't put on the slide, but there were a few teams like 971 and 900 who had started doing much more complicated vision systems where they were actually like tracking elements of the field that weren't designed to be vision targets. So they were actually tracking like the actual tape lines and logos and things that were on the field, and like some of the decorative panels and other things like that. With their much more complicated and much, they're way harder to actually implement for any other team who wasn't like writing all their own custom software. They were starting to do a lot more to where they could actually mostly know where their robot was on the field just from their like camera systems, or get a much better idea of where their robot was on the field from their camera systems. And so as they were pushing for this more technology, and we're kind of like, more people were talking about it, more people talking about trying to figure out how to do it, because the advantages of doing it started to make sense. Because if your robot knows where it is, you can really easily aim to the target. You could like automate some things. It could drive on its own potentially. It could like do a lot more different stuff if it knows where it is. So first came out prior to the 2023 game, and announced that they'd be introducing AprilTags that year. Gave us an idea of how like the technology works and stuff, and gave some time for Photon Vision and eventually Limelight to release different software things to work with those two applications. And then other people are still running custom stuff even today. But those are still the main ones that people are using. So for 2023, they had a hybrid. There were still some retroreflective tape targets. They were on the cone poles in 2023, and then there were also AprilTags. And so the AprilTags were also on the scoring location, on the cube scoring location, and on the human player shelf score game piece entry area where you could give the robot the game piece. And so we had some idea of how these like AprilTags would work, and they worked well enough in 23 that in 2024 they completely eliminated retroreflective tape and moved exclusively to the AprilTags. Okay, so let's talk a little bit about how the AprilTags. Oh, actually, before we do that, we can look at the last bit of vision. I forgot the slide existed. Um, so before AprilTags, the vast majority of the vision systems were only really there to help you like point directly at where you're trying to score. So either they were those color things we talked about, or they were all of these different retroreflective targets, and they were almost exclusively only around the actual goals where you were trying to score. They weren't anywhere else on the field. Sometimes in 2019, there was also on the human player zone, so some of them were on where you were trying to like get game pieces, but rarely were they just somewhere else, not on one of those things. So this is the 2013 goals, so they had them fully around the boxes of the different goals, and so you could light up that whole box and track where it was. In 2019, they had these little hash mark retroreflective tapes on each of the different scoring locations. And then in 2022, this one was actually pretty tricky for a lot of teams. I think we ended up just copying code out of that Mechanical Advantage 6328 wrote, because it had these little lines, but it was like going around in a circle. So the way the camera picked up these rectangles was very weird. To actually try to find the center of the goal was a pretty computationally complex thing to do. Is you had to like look at each corner of these different tape lines that you're coming back as squares, and trying to figure out how to actually like make it into a circle that you could then figure out how to computate the middle of that circle. So there's a good amount of like math to try to figure that out. Mechanical Advantage had some very smart people do some of that, and we were able to use that code to make our robot work a lot better. Because once you know the center of that circle, you can know how far away you are, you can aim to it, and you can adjust your ball launcher. They said in that game you had to launch balls into here. So we were able to adjust the speeds of our launcher and the angle of our robot towards the goal, so that ideally every time we released a ball, it always made it in the goal. And we were able to do that really accurately, in large part because we were able to know exactly where the center of that goal was from the cameras we were using. If we didn't have that camera system, it would have been a much harder season to actually scoring points and getting good use of the balls into the high goal and things. It would have been much harder to do. Okay, so in 23 and 24, especially 24, since this is the first launching game with the new AprilTags, where we have to be able to aim at a goal really easily. In 23, you were just placing the cubes and cones. It still was very helpful, but you could definitely do quite a bit of it manually. You're scoring like right up on the driver station window, where here there's a lot more going on in this game in 24. And so more teams were using the AprilTags to as the full advantage that they could, to where they were basically allowing us to fully know or approximate, estimate where the robot is on the field all the time. So we're going to talk a little about how that actually works, and what we're able to do with that moving forward, and why it's so important to all of our, basically every season going forward. A good amount of the work we do is on that pose estimation and using the AprilTags well. And so even before we have a robot built, we'll have people on the team who want to be doing the vision things, using some of the past robots and making sure we have our practice field set up to where we have the tags in all the right places. And so we can be making sure we're getting that pose estimation really well done, just because there's so many things we can do with it to make our point scoring and robot more efficient during each match. Okay, so we've talked about AprilTags, but we haven't actually talked about what they are. So AprilTags are, in the easiest of terms, they're a very basic type of marker tag, similar to QR codes, except they have very little information in them. So that makes them very easy for the robot to see and identify. And very fast for the robot to identify. So QR codes work great with your phone, right? You can hover over it at a menu at a restaurant or whatever, and you can get that URL to see what you need to see, and it has the full information of that URL in it, and you can go and get that link. The problem is it does take a second to actually fully identify. And if you swipe your phone over it really fast, it's probably not going to get the right QR code. It's probably not going to identify anything. With QR code, or with AprilTags, because there's very little information, they just have basically specific patterns here that identify just the ID number, so that when the robot sees this, it only knows that this is ID 1. That's all it cares about, and this is ID 2, and this is ID 6. And they're designed to be very it's very hard for the robots to mistake them. That's why they look a little bit different. They're designed specifically so that the robot will never see ID tag 2 and think it's ID tag 1. And there's a whole host of different versions of these. There's different families, so you can have a larger number of them, but they get a little bit more complex, where they have slightly smaller squares inside them and things. Same with the actual size of the tag itself can help determine how fast the robot can see it and identify it. But as long as they are standard, so the first is basically set up a standard size for the tag, um, and so we can either like print them out ourselves, or we can buy versions of them that we have like vinyl stickers that print on the polycarb the same way that First does the official ones. And with these, we First puts them in very precise locations on the actual field each year. So we had these 2 that were on each of the speaker tags here. And then there were also tags on the loading zone on each face of the stage where the robots were climbing this year. And there was one on top of the amp as well. And so with those precise locations, that allows us to basically like have a map of where all of those tags are. This same technology, the original AprilTags were developed many years ago at, I believe, the University of Michigan, and it's used for allowing robots to estimate their position and be able to navigate different environments. So we're starting to see them more. If you like look even at like Walmart, you'll like walk by a pole or something, and there'll be one of these little tags on it because they use them for like automated floor cleaning machines and things like that. And so other stores and stuff are starting to use it to help with actual industrial robots and other automated tasks as well. So they get used in warehouses and things too, so they can navigate, know which row or aisle, or where the robot is, or what it's looking at, or how it's identifying things. Okay, so um, this is definitely just going to be the overview. We're not going to like dive into any of the code or anything, but it is useful to have some idea of what the tags are actually doing and what the robot's doing with that information. So again, the tags are always in a very precise location on the field. That's also why we have time before each event to do field calibration, so we can actually measure how the field is actually set up and built, because each of these fields are built like basically the day before we compete on them. They're not permanently set up anywhere. So they do move around a little bit. And so knowing where the tags are is pretty helpful. And so if for some reason a tag is placed really far off, we have to make sure the field crew knows and they can adjust it and get it back into the right place. But yeah, so if we assume we know the precise location of all the tags, we also know the location of our cameras on our robot. So that's actually part of the important part, is we have to mount our cameras in a way that in CAD we can tell very precisely where that camera lens is from the origin, like center floor of our robot. And then we also know things about our camera, so we know like how the lens works. And we also know, I think I already mentioned it, but we also know exactly the size of the AprilTag itself, like the physical size of the AprilTag is really important. And if we know all those things, we can then calculate the position of the tag in the camera's field of view, and use that to get an estimate of where the robot is on the field. That process is basically what we call pose estimation. So we don't know exactly where the robot is, but we get an estimate of where the robot is based on the camera and each of the tags it sees. And so we can kind of triangulate back, where do we think the robot is and what way do we think it's facing, like how it's rotated or anything, to the tag that we're seeing. So if any of those steps are off, though, the estimate of where the robot is going to be off as well. So if the robot's moving really fast, if it's shaking, if like the camera mount's vibrating, if the tag itself is moving a little bit. So this is actually a problem we ran into this year. There was the tag that was on top of the amp. The whole amp would swing back and forth. And so that tag's location would literally be moving. And so it was really hard to use that tag. So we actually had in our software to just ignore that tag. Even if the camera saw it, we were never trusting it to give us a position, because we could never know when that tag was actually located on the field, because it was moving, 3 or 4 inches front or back, just because that whole structure was shaking. And so this happens sometimes if we go to like, as you go to like different practice fields and things, the AprilTags may be in different spots, so that can change things. If the walls are angled at all, anything like that, it can change how the robot behaves, or based on where it thinks it is in relation to everything else on the field. The picture over here, you can kind of see an idea of what the vision system is doing. It's kind of tracing the outside of that cube and figuring out like what angle it's kind of facing away from the robot, because it knows the actual size of the tag. And so when it sees that, oh, in this image, this is a much shorter leg than this is, that means this tag has to be like rotated away from it at this certain angle. And so it's able to use that information to get a much better idea of where the robot is on the field. So we have this idea of like the vision system telling us where the robot is. But our robot knows more stuff than just what it's getting from the cameras. One of the most important things that it knows is called odometry. And odometry is just a fancy word for counting rotations. So we basically, at the beginning of the match, we assume that we know where we're going to start the robot. So this is how we're able to set up our autonomous modes and things. We know pretty precisely, or we try to precisely place the robot in a very specific spot on the field, so that from that spot, if we rotate the wheels all one rotation backwards, we'd know that we're exactly one circumference of wheel distance away from where we started. And since we know we have like the encoders are the sensors built into the motors, and so we can sense how many rotations like each of our motors has spun. We can know how far the wheels have rotated, and we can know which direction they're pointing based on the steering motor and its encoder. And if you take all of that stuff and combine all of that knowledge of how motors are spinning, we can get a pretty decent idea of which direction and where the robot has moved from where it started. The problem is that's not perfect. If you just use wheels, if you just use the wheel rotations of the motors, you get an okay idea of where the robot goes. And if it's just driving very slowly and smoothly, it would do a pretty good job of telling you where the robot is from where it started. But we use a little bit more information to help with that. So we use a gyro that we talked about on Monday. And so the gyro can sense how much the robot has rotated. And that's pretty important too for knowing maybe if we're trying to drive straight back and somehow things don't go exactly right and we start slipping some degrees, the gyro will help know that, and it'll calculate that, oh, we are returning a little bit, and we can use that to kind of keep us straight. We can also use that in our calculations of our odometry to know where the robot's going. The problem is, again, this only kind of works if everything is working exactly perfect. And the robots are definitely never exactly perfect. So one of the biggest issues is what we call wheel slip. So if at any point any of the wheels are turning more than the robot's actually moving, we no longer know where the robot is or how far it's traveled. And so this can happen for a whole host of reasons. If we just accelerate too fast, if you just give the robot full power backwards, depending on how everything's designed, how heavy your robot is, what type of wheels you're using, the wheels may just slip on their own, just like if you'd imagine the robot doing a burnout if it was a car, right? Like the wheel may spin a little bit before the robot actually ever moves in that direction. And so those little bits of rotation where the wheel's moving but the robot's not still get added up into our odometry calculation of how far we've traveled. And so those errors build up. The gyros themselves will have a little bit of drift in them. So if you just run it for long enough, even if you just left it sitting still, it would slowly drift a little bit over time. Modern ones that we have now, like the Pigeon 2.0 and the I think it's the Canon gyro, whatever it is from Redux. They're both pretty good about not having a lot of drift. So you don't see a ton of it, especially like stationary drift at all. But where all of this comes into, as soon as other robots start running into us, it gets a lot harder to know where we are, as we may be trying to drive one way, but we get another robot to hit us, and now some of our wheels are just completely off the ground, and they're spinning, or we get spun really fast somewhere. And so as soon as you take a really hard hit, your odometry values always get pretty far off of where you think you are, which direction you're even pointing sometimes. Can all change a little bit during the match. And the robots definitely hit each other. The robots definitely run into other things. Um, and so that whole odometry value of where we think we are based on where we started isn't very perfect. And so we can combine the odometry, which is very good at like intermittent things. Even if we can't see an AprilTag, we can have a good idea of where we are between the times when we have a good idea of where our location is. Um, and so we do a lot of math, and that's a lot of what we do when we're talking about like tuning the vision system. Is we have to decide how much do we trust all of the different ways that we can approximate where our robot is. And so we use odometry and pose estimation from the vision system. And we add in those vision estimates basically to give us a better idea of where the robot is on the field throughout the entire match. Um, Part of that is trying to figure out and understand, when does each system know where the robot is at different times or at better times. Um, we literally call it trust. So a lot of times when we're feeding in those pose estimates into the odometry, we have to decide how much do we actually trust each of those vision estimates. If we could trust it 100% all the time, anytime we saw an AprilTag, we would fully just ignore odometry and say, yes, our robot is exactly here. The camera's told us. We know where it is. It would be great if it was that easy. It's definitely not that easy. So a lot of times we're choosing based on different things about what the camera sees to decide how much to trust it and how much to add in that value, or like adjust where our odometry value is based on the camera estimate of where we think we are. Um, it would also be a problem just because it would bounce the pose around a lot. Like if we're not trusting our wheels at all, and we're just trusting like every camera tag. If a different camera saw a different tag, or the same camera saw another tag, it might have slightly different pose estimates. And now our robot thinks we're just like hopping around the field. Even if it's in a small area, that could mess things up, right? If it thinks we just moved 5 inches in an instant, certain parts of the code and things would just not like that, and it wouldn't work very well. So we want to roughly smoothly adjust our odometry value back to correct whenever we can. Yeah, and if we don't trust them at all, then we're not using our vision system well either. So we want to there's some middle ground of deciding when the camera is doing a good job of giving us an estimate, and we trust it then. And when the camera is doing a bad job, we ignore it as much as we can, and we trust the odometry alone. Or we try to have multiple cameras, so we're getting better estimates from a different camera. Maybe one camera is blocked or doing something different, or just not getting a good estimate. If we have another camera on the other side, that one might be giving us a better signal, and we can know to choose to use that. So some of the things we use to trust, to decide when to trust those camera estimates, and we basically like tune these throughout the entire season. So this is a lot of what we're doing as we're trying to improve our vision system from the beginning of build season, when we find out the game and like know where all the tags are, all the way through the world championship. We're kind of changing these weights of how much do we trust each of these different measurements, and like deciding new ways to classify different measurements. So some of the times, if the robot's moving really slowly, the camera estimates are normally better. If we're not moving really fast, we can like have the same camera estimate for a long time, and that's normally allows us to move to that estimate better. It's also true if we have like multiple tags in view, the camera can do a lot of the math on multiple tags and get a much better idea of where the robot is. Same if the tags are super close to the robot, so it's really big in the camera's view. it's a little bit better at doing those calculations too. If the tag's really far away, it's a lot harder to know just because like a single, pixel could be different and that might change the math of where the robot is. So having more tags in view, having the tags closer, the robot moving slower, the robot not rotating very fast, um, all of those things are things that we kind of adjust and change and decide how much do we trust a single estimate based on all of that information we have about the estimate and like when it's taken. Um, the other thing I didn't put on the slide that is actually really important is we also have like some amount of delay or time between like when the estimate is taken and when we decide to change our position. And that can have a whole host of issues and cause problems, or if you do it right, can make your this whole process smoother. Is knowing how long does it actually take from when the camera takes the picture to when we're doing like the math and deciding to change our location based on its estimate. Because if you're really slow, the robot might already be, several inches to several feet away from when that picture was taken. Most of the time it's not that far, but even small amounts of lag add up and build up to where you just accumulate error over time, and you're just never right in that right spot. So being able to get rid of some of that that network latency or that lag between when the estimate's actually done and how long either the math takes or how long the information just takes to get to when we're actually trying to use it is pretty important as well. Okay, so what do we do now? So we already kind of talked about them, but we'll kind of talk about what the modern solution is and what we're using is Limelight and Photon Vision are both set up really nicely right now. We've been using Limelight for a long time. We had like 5 of them on a robot last year. They can both track AprilTags well, and give back that pose estimation that then we use to influence our odometry. We no longer need those bright LEDs to do goal tracking anymore. So normally they're not shining at driver stations, which is nice. The cameras have changed a little bit. So we used to need color cameras because we were trying to track those like green blobs and green shapes in our in the camera's field of view. But now with the AprilTag, since those are black and white tags anyway, there's a technology that lets us make motion blur go away. So global shutter cameras, I'm going to give like the 2-second version of what they are. But you can look it up more if you want to dive deeper into it. They basically are able to take the same frame of like all of the pixels of the camera at the same time, so that even if the camera is moving really fast, you don't get that kind of blurry image that you'll sometimes get with cameras, just because different parts of those pixels are being, different parts of the picture are being taken at different points, even in the video. And so the global shutter definitely helps a little bit, so our robot can see the tags even while it's spinning or even while it's driving fast. It can get and identify that tag a little bit better than it can with just the normal color cameras. And then now as well, instead of just having the cameras just pointing at like where we're trying to aim, so normally you would just have a camera pointed like in the same direction as your launcher. Teams are now starting to have a lot more cameras because you can, even if you can't see the target, even if you're front camera and you're not facing the goal, if one of your cameras can see any of the AprilTags, you can know which direction the goal is, since you know the position of the goal on the field and you know the position of the robot on the field. We can use that to quickly turn around and aim at the goal, even if we're not actually seeing the goal in our like aiming camera's view. So that's a lot nicer now, and so we can use that to do things like last year, when we were feeding, when we were coming out of the human player station and we were just throwing the notes over the stage to our alliance partners that were playing the front zone and actually doing the scoring. We could use our position on the field to know how to aim at the right spot, know how far away we were from that spot, to be able to change like our launch angle and things, so we can kind of place the note in as close to the same spot as we could every shot. Um, so we didn't even really have a goal to look at all. We were just using our position on the field and our position estimate on the field to try to aim at a specific spot on the field that we could then launch at. So this is actually, we changed some things when feeding became more a part of our game. We changed like our back, we added like the back camera and changed where it was pointing so it could more easily see the April tag that was on the human player loading station, the source last year. So that when we were driving away from it, we could have a better idea of what our position estimate was. As with our initial position, we couldn't really do that, and we were like losing some of that position, and it wasn't able to precisely launch the notes where we wanted them to. So having multiple cameras is definitely helpful. The cameras on the side helped a little bit. So if we were turned sideways, or if we were able to have one of those see one of the stage tags, we could have a better idea of where that robot was the whole time. So we don't know what's coming in 2025, but we assume there'll be April tags on the field again, and we'll be able to kind of build on what we learned last year and some of the stuff and the routines and things, looking at some of the other teams' code and how they do it, to be able to precisely know where the robot is on the field is the goal. So yes, you can either, so teams who are doing this at high levels either have multiple limelights, or you can also have multiple setups with photon vision and do the same thing. There's even ways to have both of them combined as well. So that's one of the things we might be doing, is having some amount of a photon vision computer, because it does some things differently, or is capable of doing some things that Limelight isn't. And so there's some reasons where we might want to have that as well as some of the Limelights on our robot. And there's several very good teams who were playing on Einstein who don't have any Limelights on the robot. They just have photon vision setups, or custom vision setups that are running on these single board computers with like USB cameras plugged into them. Okay, so that's all the pose estimation side. In addition to that, we've also, just because technology has changed and kind of how the software's worked, we've been able to do a lot more object tracking in the last 4 years as well, maybe a little before that, but really like 2020 till now. We've been able to actually track the game pieces on the floor in addition to just tracking our targets in the field itself. So both Limelight and Photon Vision have the ability to do this, so we can use our cameras to point them towards the ground, kind of in front of where our intake is, and we can detect the game piece and detect different objects, and use that to be able to aim our robot at the game pieces. This is one of the cases where we still might use the additional lighting. So like on our competition robot last year, we did have the bright green lights, but they were kind of pointing down to the ground so that we could light up the notes in the carpet and get a little bit more contrast there, and have a little bit more consistent lighting so we could see them without having to tune a bunch based on which venue we were in or anything, versus like, right, the lighting in our lab that has like the little LED lights or whatever is going to be very different than the lighting at a big arena or something like that. So getting the green light does help, and we can do a little bit of that during field calibration. We can change some of those settings and things so that the robot knows what the specific orange is going to look like for the note last year or whatever the game piece is in the future. And it does do this, both of them do this using AI in quotes. They are building basically neural networks, which is a form of artificial intelligence, where they're able to train on a whole bunch of images of the different game pieces. So normally at the beginning of the year, people will like go around asking for people to take a bunch of pictures of their whatever the game piece is that year and submit them to them, so they can use all of these different pictures of the game piece to train that model, so that when the orange ring comes into the image, it can identify it and say, yeah, I'm pretty confident that's a note. And so we can use that to detect a whole bunch of different objects. You could do the same thing with cones and cubes in 2023. We had versions of it somewhat running in 2020 for the yellow power cells. I don't think we ever had it on the robot for that year, but that year was also cut short. But we did use that this year to be able to identify the notes for some of the different auton modes if we wanted to not go out and grab a note if it was already taken off the center line, or in teleop if there was a spot where the pilot couldn't see the note, so like that deep corner sometimes, depending on what driver station you were in, we could hit a button and it would turn the robot towards the note, get it centered, and drive in and try to grab it, even if the pilot couldn't see it. So you can do some of those things with the cameras as well. They're normally not as beneficial as the position the pose estimation, um, but it still can be very useful. So having that object detection um, built into both those systems is pretty nice and allows us to do quite a lot of stuff um, with the cameras. Okay, so that pretty much wraps up our intro. The software side of it isn't as complex as you might think. So much of it is done for us in the libraries now. So both Photon Vision and Limelight have a lot of the actual software to identify the AprilTags and like which number they are. All of that's pretty much done, even including like how they're skewed and like which way they're pointing, all the way to like even getting back the estimates for the robot. Most of that's basically already done for us. Those are solved problems. Those were solved by researchers in university labs for years, and then some people doing it in the open source community and things as well. But a lot of what we do is make sure that we can actually communicate with those two things, get back those pose estimates, and then do the actual software of how do we integrate it into our odometry, and then how much do we trust it, and kind of tuning all those values and choosing when to trust those things is pretty important. So a lot of it is just kind of connecting things together, making sure it works, and then a lot of tuning to try to get more and better estimates so that if the robot has a better idea of where it is on the field, we can have a better idea of how to score into the goal because we know where we're aiming. I kind of glanced over this briefly, but there are teams, you don't have to necessarily go all the way to pose estimation. We chose to make sure our robot could do it and we could like shoot blind if we needed to. But a lot of teams do just use the target itself, similar to how teams were using the vision targets. So you're able to just like see the target, and then you can tell it to like center the target in your field of view and then aim that way. So that is an option for how to do it, and there's some games where that might be better. I think even 254 was using different versions of doing some amount of that where they were just kind of aiming at the specific target, or versus the full pose estimation based on what the camera was seeing at the time and different tasks and things like that. So they have some examples in their one of their Chief Delphi threads explaining some of their robot about how some of their code works for that. And there are quite a few teams who are able to get by just kind of having that aiming directly at a single tag. So there are a lot of different ways you can do this. There are some teams who are still trying to track even more of the field, so they will like track like the red logo up here, this red triangle, and that gets farther than we've ever really tried to reach. But there are teams who do still do some of those things too to try to push vision even further. Ideally, I'd like to eventually see some cameras that are mounted like up above the driver stations and facing out that like every team has access to on the network. We don't have that yet, but it seems like it would be a pretty reasonable addition to the field costs and allow for some much more advanced vision things where if you have stationary cameras that can see all of the robots on the field, then instead of just knowing where our robot is, we could start figuring out where the other team's robots are or where our partners are. And you could do much more advanced stuff where we could like calculate how to pass an object to one of our partners or how to automate getting around defense. Or just game piece tracking at the whole field level so we could make more advanced paths for how to intake game pieces better. Like having those stationary cameras could do a lot. And the technology kind of exists to be able to stream those to all 6 driver station laptops, and you could do all of the computations actually act on the laptop itself and then feed the information back to the robot. The video stream doesn't have to be doesn't ever have to go to the robot. So hopefully one day we'll get there. So there's still a lot to develop. Right, we've come a long way from some green painted boards back in 2005 to where we actually have localization and things on the robot. But we still have quite a ways to go too.